Okay. Yes, so the quadrants are exactly the same as before. So this is our tan graph. You would plot it by table method if you'd never seen it before. There's quadrant 1, there's quadrant 2, there's quadrant 3, and there's quadrant 4 as usual, right? Starting at 0, ending at 90, okay? And you can see very clearly that tan is positive in quadrant 1. We were expecting that. And that it is negative in quadrant 2. And that it's positive in quadrant 3 and negative in quadrant 4, exactly as you'd expect. You'd also put in the asymptotes. A tan graph without the asymptotes is always going to lose you considerable marks. So when you did tan of 90 degrees, you got maths error, and that's because you were dividing 1 by 0, which is always inconvenient, right? And then there's another asymptote over here. The asymptotes occur every 180 degrees. So it's very, very important to notice that had you drawn the negative side, there would be another asymptote there and another one at negative 270, right? So, oh gosh. So you are going to have an asymptote exactly every 180 degrees on a tan graph. This is again further proof that 0 to 90 is in fact quadrant 4, right? Because a negative 0 to negative 90 is quadrant 4, right? We're going backwards. But I'm not going to worry about that for right now. So if somebody asked you what the period of this graph is, how often does this one repeat itself? Every 180. So this graph repeats itself every 180 degrees, starts again. You can see that if we're starting over here at 90 degrees down there, and then you have a full cycle between 90 degrees and 270, right? So it repeats itself every 180. What is its amplitude? Is that a term that you can use?
No.
No. So this thing is infinite. The values, if I ask you for the range, then y is an element of real numbers. Do you agree? So the range for this one is you have every single y value you can imagine. It goes up forever and ever and ever and ever. What about the domain? What is the domain? Well, yeah, it's definitely the x values, but what is this specific domain? X is x an element of real numbers anymore? No, you've got all the asymptotes, but you have all the other numbers. So x is an element of real numbers, but x is not equal to k times 90 plus 180 degrees. So what that means is every 90 degrees, you are going to, if k was equal to 1, okay, k is a constant. If k was equal to 1, then that would be, oh, sorry, I've actually got it the wrong way around. Let me change that, sorry. This is, it's not going to be equal to 90 degrees plus k 180, okay? Sorry, please change that. It's very important. It's a completely different thing. So this is the way you would express the fact that we have asymptotes. So you can see that there is no x value when x is 90, right? At least, yes, it is 90. And there's no x value when x is 270, and there's no x value when x is equal to negative 90, and when x is equal to negative 270. Do you agree? So you can't just say x is an element of real numbers because it definitely isn't. So you have to show in some way that you know that those numbers are not there. And you have to list all of them to infinity, which, you know, could take a while if you were going to list them separately. So what you do is you make a nice little inequality equation, a nice little equation to show what you mean. So this one is saying x is not allowed to equal 90. If k was equal to 0, then x would not be allowed to equal to 90. Do you agree? So in other words, I'll show you. I'll just fill it in case you're feeling a little slow. So this is saying x is not allowed to equal 90. Imagine for a moment k is equal to 0, right? Then x is not allowed to equal to 90, right? Because you're saying 0 times 180, which is true. Then if you tried k is equal to 1, then x is not allowed to equal to 1 times 90 plus 1 times 180, which is x is not allowed to equal to 270, which is true. Do you agree? If we put k is equal to negative 1 in, we're going to get this one over here, and so on, right? That one will be k is negative 2, and they go to infinity. So by doing that, you're showing clearly which x values are excluded. Forever and ever, for everything always, right? What else is important about a tan graph? I can't think of very much else. Oh, one other thing that's very important that never ever sinks in for whatever reason. This point here, if you have y is equal to tan x, if this is a 1, okay, so if there's a 1, if the value of a is 1, even though it's not the amplitude, this is always the midpoint of the first interval, always. So in other words, if this was y is equal to 2 tan x, then the coordinates over here would be 2 and 45 degrees, and so on, right? It determines when it reaches the halfway mark of the first piece of the graph, always, right? That is a point people are supposed to know, but very rarely does it sink in. So,
like the question when it asks when will tan x equal 1, was that different?
Yeah, that's when will tan x equal 1, and the answer is 45 degrees. And if you had 2 tan x, the answer would be still 45. It would be when does tan equal 2? 2 tan x equal 2, then it would be 45 degrees, right?
The negative 1?
Then it would be negative 45, right? Because remember, if you have a negative 1, tan is going to do exactly, in fact, I'll just show it to you. It's going to do exactly what the sine graphs do. There is, this is not Desmos. It's going to reflect immediately. If you change that to a negative, sorry about the wavy handwriting, it's going to do that, right? Immediately. It's going to reflect. So everything will be the opposite way around. So, like that. So if you look at this one, on this one, so this would be y is equal to negative tan theta, right, or x, and this would be now 1 and negative 45 degrees, right? So it does exactly, they all do exactly the same thing. Okay. This works the same way as every other graph you've ever done. So this is sine, cosine, tan, hyperbolas, parabolas, they're all the same, okay? What we know so far is we know that if we change that value over there, it's a vertical stretch, just like every single other graph you've done, or it's a reflection. In other words, if I have y is equal to 2 sine x, then that graph is going to be going between 2 and minus 2 instead of 1 and minus 1, right? I'm going to show you the negative parts as well. I just want you to get used to them, right? And then in terms of a reflection, if I have y is equal to minus sine x, then we know that as usual what's going to happen is the graph is going to go upside down the other way, right? So we have a reflection. So you've already explored that and hopefully know it, okay? The next really obvious one is if you have, for example, plus, if you don't put the angle in, it's meaningless, right? If you have, for example, plus 2, what does that mean? What is that?
2.
Really? So every time we've added 2 onto the equation, up 2, okay? Every single time we have added 2 onto the equation. So if we had y is equal to 3x minus 4 squared plus 6, if we added 2 on and we made it y is equal to 3x minus 4x squared plus 8, that's always been up 2, right? Amazingly enough, it doesn't suddenly change for these graphs. So that one means up 2. To draw this graph, what is often a very good idea if you're going to draw it is to draw a ghost graph. In other words, what you do is you draw the original graph, which is 3 sine x, and that should be relatively easy, properly, not the way I'm doing it, right? And I'm going to do it for a domain from 0 just because I'm a bit out of space here. So that is going between 3 and 3, because of course that's the amplitude and nothing has changed, right? And now you literally lift every point up by 2. So this one is at 0 before. If it goes up by 2, it will be at 2. This one over here was at 3. If it goes up by 2, it will be at 5, right? This one was at negative 3. If it goes up by 2, it will be at minus 1, and which I've drawn rather badly. I'm going to pop it there. And this one over here, if it was at 0, will now be up at 2. And then you basically redraw the graph and just link all these pieces together. I'm just trying to see what I've done. Mine's very ugly. Please try not to make yours as ugly as this. You would lose a lot of marks, right? But the idea is everything goes up 2. Do you notice the amplitude hasn't changed? From the midpoint of the graph to the top of the graph, so now that's the midpoint, it's still 3 units, right? Amplitude is still 3, period is still 360 before it repeats itself. The only difference is the whole graph has been picked up 2, which is hardly surprising since that is what a vertical movement has always done, okay? The last one that I'd like you to see, and you're going to try this out for homework today, is this one. I'll switch to cosine so that you can see that it's the same. So say we have, let's say we have something complicated like this. We have negative cosine x minus 30 degrees. For a start, what does the x minus 30 degrees mean? Right 30, like it has every single other time, right? It's inside the bracket, it's with the x, and it means that you're going right 30. And of course, it's going to be in terms of 30 degrees because the x values are in terms of 30. Whereas notice the up and down movement wasn't in terms of degrees because we were moving according to the y-axis, which is not in degrees, right? Another major hint for this graph, okay? If you were going to draw this graph, and I'm going to, for this one, I'm going to go from negative 360 to 360. For a start, please give yourself enough space, although the notes I'm giving you have got axes drawn on, so that's one of the reasons why I gave them to you. It'll save you a bit of time. So there's negative 90, negative 180, negative 270, and I can just squash in negative 360. On this side over here, I've got 90, 180, 270, and 360. I would suggest you use a series of ghost graphs. For a start, this first graph is going to be going through 1 and minus 1. And so what I'm going to draw first is I'm going to draw the graph y is equal to cosine x, right? So that should be fairly simple. And ghost graphs you can draw in pencil, or you can draw them with dotted lines, whatever makes, or you can just highlight everything so that you can see what's going on, right? But I would just draw an ordinary cosine ghost graph if I were you, because it's usually much quicker than trying to draw the final graph. Remember, we're avoiding table method because that takes forever. So this is the graph y is equal to cosine x, and hopefully take you a few seconds like it took me, right? Then I would do the reflection. So this is piece I would do next, right? So if I'm going to do the reflection, then this is going to look like this, and see how quick it is. When the original graph is already there, then it's going to be, try and be accurate, then it's going to be very, very quick to do the reflection. So this pink one is y is equal to negative cosine x. And if you're doing this, you should label them, right? The last one says every single point moves 30 degrees to the right. So now I'm going to label my minimums and maximums, very important. This one over there was at 0. It moves 30 degrees to the right. So this one is going to be at 30 degrees and negative 1. So it's there and it's waiting without being there, it being confusing in any way. This point over here is going to move 30 degrees to the right. It'll be at 120, right? I'm going to join them immediately so I can see what I'm doing. This point over here is going to move 30 degrees to the right. So it's going to be at 210, more or less. And so that's a maximum, so that's going to be 210 and 1, right? And I'm going to draw it there. This point over here is going to move 30 degrees to the right, so that's going to be at 300. So that one is at now 300, marking it on the axis, right? And the last point, not too sure why my graph has gone there. The last point was at 360. It's going to move 30 degrees to the right. You're not going to show it at 390 because your domain is going to finish at 360. You're going to head in that direction and stop, right? And then you go backwards and do it the other way. So this one over here, 30 degrees to the right. So that's going to be negative 150 degrees and 1. And this one over here, 30 degrees to the right. That one's going to be negative 60. So it's coming from here up to negative 60 through there, right? This one is going to go 30 degrees to the right. So that's going to be negative 240. Going to come down there. And this one over there is going to go 30 degrees to the right. So that'll be negative 330. And then it's coming up a bit, heading backwards towards 360. And do not think that there is a quicker way. Okay.